Okay, let us continue our lecture on potential. Right, so previously in part 1 of lecture 8, we have learned about the work done in moving a charge with the existence of the electric field. And the equations that have been obtained, can be written again, which is we have W equals to negative Q, integrations of E dot dl. Yeah, so this is the equations that we have learned in part 1 of lecture 8, and we have defined two important findings. The first one is the work does not depend on the path taken, and number two is that the works in a closed loop movement, works done in moving a charge in a closed loop movement will be equals to 0, which lead to this equation of Maxwell's, where we have E dot dl equals to 0. Yeah, so that should be the second law of Maxwell's. Okay, so this will be the equations, a continuation from what we have learned before, in which if we say that the total work in moving a unit of charge, work unit of charge from its initial point of B to the end point of A, we can write that the equations here can be defined to be W over Q. Yeah, we will just bring the Q to the left hand side, which will be then defined to be the work per unit charge. The work per unit charge, and it can be defined now to be equals to negative integrations of E dot dl from the point of B to the point of A. So this is defined to be the work in moving a unit of charge. Okay, so these equations, which is work per unit charge, is also defined to be a potential. Okay, it's also defined to be a potential. Potential in which the units for this potential is given by volt. Right. And because we are dealing with 2 points, where we have the initial point of B and the point of a final point or the end point of A, so we can see that this potential is is further defined to be known as a potential difference. Potential difference between 2 points A and also B. Okay, so the W over Q can be then returned to be the VAB, which is further defined to be a potential difference between the point of A and the point of B. Okay, and we can also write this as VA minus VB, in which VA is defined to be potential at A, and VB is defined to be potential at B. Okay, right. Uh, so from this equation of potential difference, we can also define a new parameter, which is called as absolute potential, or potential in short, in which if we say that the initial point of point B, or the starting point of point B, is now defined to be at infinite. Defined to be at infinite. So we can have that the equation of VAB, can be further written to be simply as VA, in which the initial point is at infinite, or we can just write this as a VA in short. VA is defined to be a potential at the point of A, and the equation of VAB that we have obtained just now can further be modified to be just written as negative integration from the initial point, which is at infinite, to the end point, which is at A, which is E dot dl integration. Okay, so this is the difference between the potential difference and absolute potential, in which it can also be said that potential difference basically is the difference between two absolute potential, in which we have a potential at the endpoint, which is VA, minus potential at the initial point, which is the VB. Okay, all right. So for this, from this understanding on the definition of potential and also potential difference, we can further use it to calculate the potential or potential difference due to a point charge. Due to a point charge. Okay, so what we have here is that in this diagram, we have a point charge of Q. We have two positions, which is at A, having a distance of RA from the charge, and a point of B, which is having a distance of RB from the charge. Okay, so our concern now is basically to find what should be the potential difference between the point of B and the point of A. So by definition, we can define that the potential difference between the point B and point A basically is the work done in moving a unit of positive charge of one coulomb from the point of B to the point of A. So if you can rewrite this equation, we're going to say that the work per unit charge, which is defined to the potential difference between the point of B and point of A, will be negative integrations, initial point, the end point of E dot dl. Yeah, so this is by definition. Yeah, the work per unit charge in moving a unit per unit charge in moving a charge in the work per unit charge that will be required from the point of B to the point of A. Okay, so this W over Q from this definition can also be returned to be the VAB, which is a potential difference between the point of B and the point of A. Okay, and it can be further defined to be a negative integrations from B to A of E dot dl, which has been stated in this equation here. Okay, so basically that is the definition of a potential difference uh, uh, between 2 points A and B due to a point charge of Q. Okay, so now we know that from our discussion in chapter 2 before on Coulomb's law, that the electric field intensity E produced by the point charge Q is given by this equation. Yeah? E field is Q over 4 pi epsilon naught R squared direction of R. Yeah, and we can further write that due to the E, which is having the R direction, your dl will also be in the R direction only. Yeah, because it's a dot product, right? The E dot dl is dot product. So if E is having the R direction, dl must also be in the R direction. Yeah, that's why this dot product will not be zero. Okay, so from this known value of E and dl, we can further use it to calculate the potential difference between 2 points due to a point charge. Yeah? Okay, so from here, we can write that your VAB, yeah, will be equals to negative integrations of Q over 4 pi epsilon naught R squared direction of R dot dr direction of R E dot dl. Yeah? And this integration will be taking as a distance of point B, initial point to the charge, which is the RB, and A basically is a distance from the point of A to the charge, which is defined to be the RA. Yeah? So if we further integrate this equation, we're going to have Q over 4 pi epsilon naught integrations of 1 over R squared dr, and we can change or we can cancel the negative sign by just change the range of integration, which is from RA to RB. So that will give us Q over 4 pi epsilon naught 1 over RA minus 1 over RB. Okay, so that should be the potential difference in both units between 2 points. Yeah. Yeah, which means that potential difference between 2 points A and B due to this point charge Q is defined to be Q over 4 pi epsilon naught 1 over RA minus 1 over RB, yeah, in which B is the initial point or the starting point and A is the end point. Okay, so from this definition, VAB, we can further obtain the absolute potential value, yeah, the absolute potential value, okay, in which if we have a B, this point is said to be located at infinity, infinite position. So the equation here, we can be written as VA simply as Q over 4 pi epsilon naught 1 over RA. Okay, which means that if you base on this calculation, if we have a charge q, we have this point, let's say the point of A, and the distance is given by RA. So we can see that at this particular point of A, at this particular point of A, we can further write that the potential at this point of A due to a point charge of Q can be simply written as Q divided by 4 pi epsilon naught of RA, in which RA is a distance from charge Q to the point of interest. Okay, yeah? So now we have defined the equation for the potential at a single point, yeah, potential at a single point, or also known as absolute potential at a single point, due to point charge of Q, yeah, due to a point charge of Q. So that's why if we have these 2 points, A and B, having a distance of RA and RB from a charge Q, we can then write that at this particular point, the VA is Q over 4 pi epsilon naught of RA, whereas at the point of B is given by VB equals to Q over 4 pi epsilon of RB. Okay, so this is the absolute potential, yeah, at point A and at point B. So from here, we can further obtain the potential difference between 2 points, where we have VA minus VB will be Q over 4 pi epsilon naught 1 over RA minus 1 over RB, which is similar to this value which has been obtained earlier. Okay, so that's why we did mention earlier that potential difference and absolute potential are interrelated. Yeah. Okay, so back to this slide again. This is as what we have discussed previously, that if we consider that the point of B, yeah, previously when we have the VAB from definition equals to Q over 4 pi epsilon naught 1 over RA minus 1 over RB. Okay, so if we see that the initial point is at infinite, yeah, so B is at infinite, so we can have that the VA simply will be Q over 4 pi epsilon naught 1 over RA. This is defined to be potential or absolute potential at the point of A. Okay, so that's what we have defined earlier, yeah? Okay, so now we can say that if you are having a system of charges, let's say we have 2 point charges, Q1, Q2, Q3, and Q4, and we want to find what should be the potential value at this particular point of A due to this system of point charges, where the distance are given by R1, R2, R3, and R4 for these 4 charges, yeah? So we can see that from our understanding just previously, from the concept that we have learned, so potential at A due to charge of Q1 can be further written to be this equation. Okay, so that should be the potential at point of A due to charge of Q1. Okay, right, and then we have potential at point A due to charge of Q2 shall be given by this equation. Yeah, it just depends on the distance from the charge to the point of A. The same things apply for a potential at point A due to charge Q3, which is given by this, yeah, given by this. And finally, potential at point of A by a point charge of Q4 will be based on this equation. Yeah, we just need to know what is the distance from a charge to the point of interest. So from these values, we can say that the total potential or absolute potential at the point of A can be obtained by simply adding all of these values, in which potential at A will be given by this summation, and we're going to have this equation here, which is summation of Qi over 4 pi epsilon of Ri, in which I is taking a value from 1 to 4, since we have 4 point charges here, yeah? Okay, so this is the concept of potential and potential difference due to a point charge or point charges, yeah? Okay, so let's have a look at this example. We are having a 60 microcoulomb point charge, which is split into 2 equal charges. located at 180 degrees intervals around a circular loop of radius 4 meters. Find the potential at the center of the loop. Okay, so if we can re-sketch this problem, the charge is here. I mean, initially we have 60 microcoulomb, then it is been divided into two equal charge amount. So it means that we have 30 microcoulomb here, and we have this 30 microcoulomb here, and both charges are separated 180 degrees apart. Yeah. So the loop is having a radius of 4 meters. So we need to find what should be the potential at the center of the loop. Yeah, here, at the center of the loop. So from what we have learned before, the potential, yeah, the question is to find the potential or absolute potential. So from what we have learned before, potential at this position, yeah, V, I can just put at the V naught, yeah, because we are dealing with the origin, yeah, the center. So V naught can be written to be a summation of two potential, which is potential number one and potential number two. So let us write that potential number one is due to this charge of 30 microcoulomb here, number one, and number two is due to this 30 microcoulomb here. Okay, so that will be equals to 30 microcoulomb divided by 4 pi epsilon naught. Yeah, we are using this equation, yeah, V equals to Q over 4 pi epsilon naught of R, yeah, using this equation, yeah. Right, so remember, yeah, V is a scalar, yeah, it's not a vector, V is a scalar value. It just have a magnitude. Okay, so for that, we can just write that we know that the distance is 4, so we have 4 here. And the same thing applied for the V2, where we have a 30 microcoulomb and 4 pi epsilon naught of 4 still. Yeah, 4 is the distance from the charge to the origin. Yeah, so we're going to have that the total potential at the origin or the center of the loop will be 2 multiplied with a 30 microcoulomb over 4 pi times epsilon naught of 4, which will be 16 of pi epsilon naught, and that will give us a value of 30 micro divided by 8 pi epsilon naught in the units of volt. So that should be our potential at the center of the loop. Okay, right. So let us have a look at this example number 2. We are given a 3 point charges. We have a 1 millicoulomb, negative 2 millicoulomb, and 3 millicoulomb located at this position 004, negative 251, and 3, 4, negative 6. The question is find the potential Vp at 1, negative 1, positive 1, and 2. Okay, so let us sketch the position of these charges. We have 1 millicoulomb located at the point of 004, okay, 004. Then we have a negative 2 millicoulomb located at negative 251. And then we have the third charge, which is 3 millicoulomb located at 3, negative 4, and 6. Okay, yeah. So the question is, need to find the potential at this point of P. So I just label P here, which is located at the point of 1, negative 1, 2. Yeah. So that should be the location of the point. So need to find the potential here. Yeah. So the question is what the potential at point of P. Okay. So potential at point of P. So we know that we are having 3 point charges. So each of these point charge will incur a potential at the point of P. So we label this as V1 from negative 2 to P. From 1 to P, we label this as a V2. And from 3 millicoulomb to point P, we define to be a V3. So we have 3 different potential value incurred by different charge amount. Yeah? So Vp will be then returned to be V1 plus V2 plus V3. Yeah? So that should be the total potential at the point of P. Okay, so we can write that the V1, which is due to this negative 2 millicoulomb, we can write this as a negative 2, yeah, from equations of V equals to Q over 4 pi epsilon of R, yeah, due to a point charge. So that should be negative 2 divided by 4 pi epsilon naught. So we need to obtain the distance from negative 2 to the point of P. So from these point, I mean from the coordinate, we can write that the distance will be equals to, okay, that should be 3 squared plus 6 squared plus 1 squared. And that should be equals to set of 9 plus 36 will be 45. So that should be set of 46. Yeah? So we're going to have that the distance r will be set of 46. Okay, plus the V2, which is due to 1 millicoulomb. So that should be written to be equals to, okay, that should be 1 milli, 1 milli. So that should be negative 2 milli just now. So 4 pi epsilon naught. The distance will be set of 1 squared plus 1 squared plus 2 squared, which will be equals to set of 6. Yeah. So we're going to have that should be set of 6 for the distance between the 1 millicoulomb and P. And finally, for the V3, we're going to have a 3 millicoulomb charge amount divided by 4 pi epsilon naught. And the distance from 3 millicoulomb to the point of P is given by set of 2 squared plus a negative 3 squared plus 4 squared. Okay. Okay, how can we obtain this one? Simply we just subtracting the coordinate. 3 minus 1 will be 2, negative 4 minus negative 1 will be negative 3 squared, and 6 minus 2 will be 4, yeah? So we're going to have set of 4 plus 9, 13, 13 plus 16 will be 29, yeah? Okay, so we have a set of 29 as a distance from 3 millicoulomb to the point of P. Okay, so that should be your total potential calculated at the point of P due to these 3 point charges. Yeah, yeah. So I left this for you to calculate on the amount of potential. Okay, so for part B of the question, which is to calculate the potential difference VPQ if Q is at 1, 2, 3. So basically we are repeating the same problems here, in which for part B, you need to first obtain the VQ. Yeah, need to obtain the VQ first, in which the VQ calculation should be similar to what we have done here. Yeah, so previously we are calculating the VP. So now you have to calculate the VQ, in which you are using the same method. You have to find the distance between point from the charges to the point of Q, yeah, as we have done here. And then you need to find the VQ potential, and afterwards you can then calculate the potential difference VPQ by simply subtracting the potential of P and Q. So that will give us the VPQ. Okay. All right. So I think for part B, you can try to solve this on your own, as long as you understand the first method, the first question just now. You must be able to calculate the potential at Q, and afterwards you can simply use both VP and VQ to find the potential difference. Yeah. All right. So previously, what we have done is we have calculated the potential, yeah, due to a point charge and also due to point charges. Okay, we have agreed on the equations used, yeah, and we have defined the equations used. So now we are migrating towards another case in which we want to calculate what should be the potential due to the charge system. Yeah, so the charge system will include the line charge, the surface charge, and the volume charge. Okay, for instance, now if I have a surface charge here, which is a rho s coulombs per meter squared, given in diagram here, and we have a single point of A, the question is what should be the potential at the point of A that should be incurred by this particular charge density of rho s coulombs per meter squared. The same things apply. If you have a line charge, if you have a volume charge, and if you have a single point of A, what should be the amount of potential that will be incurred at this particular point due to that particular charge system? So that should be the things that we want to solve here, yeah? Okay, so we have agreed from the previous slide that this is the equation of potential due to point charges. if we can recall back, let's say we have a charge Q1, we have charge Q2, charge Q3, and charge Q4. We have a single point of A. So each is having different potential amount. Yeah. So we have a, for this will be Q over 4 pi epsilon of R1. Yeah. Q over 4 pi epsilon of R2, and subsequently applied for Q3 and Q4. If we have defined that at the point of A, the total potential will be just a summation of this Q over 4 pi epsilon of R. Okay, yeah? So we are going to use this equation to formulate the equation due to continuous charge distribution, in which this summation, if we can have a look at this particular slide here, we have a modification from this equation where we change from a discrete to a continuous. Yeah. So these point charges are considered to be a discrete system, but for these charges, the line charge, surface, and the volume, those charges are considered to be continuous. Yeah. So few modifications need to be done, in which what we did here is that we change the summation sign here. Yeah, summation sign for a discrete to a integration. Yeah, to cater for the continuous charge distribution, in which we have these changes for this integration sign, and afterwards the Qi in discrete is now changed to a dq, which is continuous, and Ri is just changed to R. Okay, so that should be the equation that can be used in calculating the potential at a single point due to a charge system, a dq over 4 pi epsilon of R. So the dq will be depending on your charge structure, yeah? Whether it is a rho L dl for the line charge, whether it is a rho S ds for the surface charge, whether it's a rho v dv for a volume charge, yeah? Okay, so this is how we have defined just now. So potential at point of A will be written based on this equation, where initially we have a dq, so it's now written to be rho L dl. A surface charge is written to be rho S ds, and the volume charge will be written to be a rho v dv. Okay, we can also use this equation then to calculate the potential due to a continuous charge distribution, the line charge, surface charge, and the volume charge. Okay, and also remember, yeah, this is a potential, yeah, potential at the point, or defined to be an absolute potential. Okay, all right, and also we can also use other method, which is we have to go back to the basic equation where we have V equals to negative integration. Let's say at the point of A, yeah, the point of A, the potential at the point of A is defined to be negative integration from infinite to the point of A of E dot dl. Okay, so we have two options now to calculate the potential, either to use this equation that we have defined, okay, these three equations depending on your charge distribution, or we can also go back to this basic equation which have been used before, where the potential at point A will be negative integration from infinite to A of E dot dl. Remember, yeah, because potential is a condition whereby your initial point is at infinite. So that's why we have the integration from infinite to the point of interest. Okay, so we have two options to calculate the potential, either to use this or you can use this equation. Okay. Okay, so let's have a look at this example just to test our understanding on the potential concept. Okay, so we are given this expression, obtain the expression. You need to find the expression for the absolute potential, yeah, absolute potential, along the z-axis of a ring uniform rho L coulombs per meter and whose radius is R0. The ring is located at z equal to 0, and it's given that the electric field at any point on the z-axis is given by this. Okay, so we can actually use two methods to find the potential, yeah, to find the potential or absolute potential at a given or requested position, which is along the z-axis, yeah, z-axis of a ring. So which means that if you can sketch the problem, You can change the problem should look like this, where we have, this is the X, that should be the Y, that should be the Z. So your ring is look like this. Okay, so that should be your R naught, the radius of the ring. That should be the ring, yeah, in row L. Yeah, yeah, that should be the ring. You need to find the potential at this position, any point, yeah, on the z-axis. Let's say we define the point to be 0, 0, z, yeah. So z is a variable. Okay, so need to find what should be the potential at this position. Okay, so based on what we have learned previously, we can use the first method in which we use the V equals to integration. Yeah, V is potential here, yeah, at the point of 0, 0, z. So if I can label it, so this is what we're going to find here. Potential at this point is given by rho L dl over 4 pi epsilon naught of R. Okay, we are based on this equation. Okay, and we can define that rho LDL basically is a small element of charge here on your ring. Yeah, so that should be the rho LDL, or it also defined to be rho L of R naught dV. Yeah, so basically this is same like what we did in chapter 2 on the Coulomb's law. Yeah, the same things that we did. So we are going to have the integration. Yeah, that should be rho L. dl will be R naught dV divided by 4 pi epsilon naught. Okay, R is the distance, yeah, it's the distance from this element, yeah, this element or your charge dq to the point of interest. So that should be your, sorry, not a straight line. I apologize, yeah, should be a straight line then. Oh, sorry, I made a mistake. Sorry for that. Okay. So that should be a point of interest, support rho LDL. So R basically is a distance, yeah? That should be a distance, yeah? And that should be R, a distance from the charge, the rho LDL to your 0, 0, Z. Yeah, the point of interest. So R is defined to be, so we know that the vector of R, we define the vector first. The vector of R is given by this vector, and this vector, which is R naught, direction of negative R, plus that vector, which is Z, direction of positive Z. And from this vector, we can straight away find the magnitude, in which R magnitude should be defined to be R naught squared plus Z squared square root, yeah? Okay, so we're going to have the R magnitude to be equals to R naught squared plus Z squared. Okay, so we can define, we can straight away do the integration, because the integration is towards the dv. So we're going to have rho L R naught over 4 pi epsilon naught R naught squared plus Z squared. Okay, and that should be 2 pi, yeah, because your range of integration, because a circular loop, a full circular structure, so it should be from 0 to 2 pi. So we're going to have the answer for that will be simply rho L R naught over 2 epsilon naught square root R naught squared plus Z squared in volt unit. Okay, yeah, so that should be the potential value that has been produced by this particular circular loop structure having a density of rho L coulombs per meter, having a radius of R naught towards any point on the z-axis, having a coordinate of 0, 0, z. Yeah, so z is a variable. Yeah, z is a variable. Okay, yeah, so that should be your potential, or absolute potential at that position. So for examples, if you want to find, let's say, if you want to find the potential, let's say at z equals to 2, for instance. So simply we can find that. So V at z equals to 2 will be simply rho L R naught over 2 epsilon naught square root R naught squared plus 2 squared, yeah, because z equals to 2. Yeah, and also if you want to find potential at z equals to 4, so we're going to have the potential at z equals to 4 will be simply equals to, yeah, sorry, equals to rho L of R naught divided by 2 epsilon naught square root R naught squared plus 4 squared. Yeah, so let's say if you want to find what should be the potential difference between z equals to 4 and z equals to 2, potential difference, yeah, between these 2 points. So what we did, we just simply subtract. Let's say this is the first equation, and that should be the second equation. The first equation is potential at z equals to 4. And number 2 is potential at z equals to 2. Simply, we just subtract the two equations, in which we're going to have subtraction of equation 1 and equation 2. So that will give us the potential difference between these 2 points at z equals to 4 and z equals to 2. Okay then? Okay, hopefully you understand, yeah, this exercise. Okay, I'm going to use the second method to calculate the potential value, okay, in which I'm going to use E dot dl method. Okay, so basically the E value has been given, in which this is based on our exercise in chapter 2 last time in Coulomb's law. So if we can sketch again the diagram, okay, so it should be your charge, okay, that should be your x-axis, that should be your y-axis, z should be there, that should be the radius of r naught, and the charge is rho l coulombs per meter. So basically, that should be location of interest, which is at 0, 0, z. And from our exercise in chapter 2 before, we have defined that at this particular position of 0, 0, z, the electric field has been defined to be this equation. Yeah, so that's your E field. That's your E field. You can check this again in chapter 2. Okay, so if you want to find the potential at this particular position of 0, 0, z, in which the E field has been given, simply we can use the equation, in general equation, where we have V equals to negative integrations of E dot dl. Okay, this is the equation that shall be used in calculating the potential. But things you have to remember on certain principle that to find the potential at this particular point, yeah, you need to state that your initial point should be at infinite. Yeah, initial point should be at infinite. So let's say we define this point to be a point of A. So the potential at the point of A will be equals to negative integration, a movement from infinite to the point of A. Okay, so that should be the definition that need to be used, yeah, in calculating the potential when you use the equation of E field, yeah. Okay, so we can proceed now. We find the potential that should give us negative integration, infinite to point of A. The E will be given by rho L R naught Z over 2 epsilon naught R naught squared plus Z squared power to 3 over 2. That should be your E. And the dl, because your E is in Z direction, so we know that because we are using the cylindrical systems, right? So the dl can be in the R direction, can be in the phi direction, can be in the Z direction. Okay, so since your E field is in the Z direction, so the R and the phi can be ignored, can be cancelled out. We just have the dl in the Z direction, in which the dl in the Z direction is given by dz of Z. Okay, so for this, we can proceed with the integration straight away, where this integration can be written here, where we have the VA, yeah, will be a negative. We just take out the constant, rho L R naught is taken out over 2 epsilon naught, yeah, and we're going to have integration of negative infinite of A, so we're going to have Z dz over R naught squared plus Z squared power to 3 over 2, and this integration will require the use of identity, in which we're going to have that the VA be negative rho L R naught over 2 epsilon naught, and this will give us negative 1 over R naught plus Z squared power of half, which is from infinite to the point of A. So yeah, the point of A, yeah. Okay, so we can proceed with the integration. Yeah, we can proceed with this substitution of the value. Okay, if I use this part here to calculate the potential at the point of A, okay, I'm going to use, I'm going to obtain that the VA will be simply equals to negative rho L R naught over 2 epsilon naught. I'm going to substitute the value. So the point of A here, I have to substitute this as Z, yeah, as a Z, because we are integrating towards a Z, yeah. So I'm going to use Z as the value for the A. So that will give us -1 over R naught squared plus Z squared power of half. Okay, and we substitute the infinite into the Z. For the second part, that will give us 0, yeah, minus 0. Okay, so end up we're going to have the potential at point A shall be equals to positive of rho L R naught divided by 2 epsilon naught R naught squared plus Z squared square root. Okay, so if we compare with what we have done previously by using an equation of integration of rho LDL over 4 pi epsilon of R, yeah, based on this equation, VA as integration rho LDL over 4 pi epsilon of R, we can prove that the equations obtained by this method and obtained by this method of E dot dl, the value, the terms of the potential at the point of A will be similar. Yeah, we can prove this. Yeah, so that should be the potential invoked by using the method of integrations of E dot dl. Okay, then, so you have two options to calculate potential, as I mentioned before. For the case of continuous charge distribution, whether you can use the equations of this, yeah, that we have defined here, depending on your charge distribution, rho LDL, rho STS, or rho VDV, or you can also go back to the basic equation, which is the E dot dl integration, yeah? Okay then, so we proceed with the example, next example, in which we are having a case of a circular shell. Find the absolute potential inside and outside a thin shell centered at the origin of uniform rho s and of radius r naught. Obtain the potential at r naught over 2, r naught, and 2 r naught. Okay, so for this, we are given a shell. We're given a shell. Okay, we're given a shell in which the shell is centered at origin and uniform rho s on the surface. So it means that we're having the surface charge density rho s on the surface of your sphere, on the shell. Yeah? Okay, so obtain the potential at this position, which is, okay, the radius for the shell is r naught as given in the question. From here, you need to find the potential at three positions. The first one is r naught over 2, which is basically inside the shell. Then we have r naught, which is on the surface of the shell. And then the third one is 2 r naught, which is outside the shell. Okay, so if we base on this example, basically we have a shell problem in which if we want to find the potential, we need to first find the E field. Yeah, because if we base on these particular problems, uh, we can find the E field. Yeah, the E field can be obtained by using a Gauss law. Yeah, because we are dealing with a symmetrical charge distribution. Yeah, spherical is a spherical charge. In this case, a surface charge is considered to be a symmetrical charge distribution. So the E field can be calculated only by using Gauss law. So if the E field can be calculated by only using the Gauss law, so the potential equation that shall be applied in calculating the equation that shall be used in calculating the potential value shall only be the V of E dot dl integration from the infinite to the point of interest. Okay, I repeat again. If you have a charge structure in which the E field can only be obtained for the using the Gauss law, which is applicable for the case of symmetrical charge distribution. If you want to find the potential of this charge distribution, you can only use the potential equation of E dot dl integration, which means that we cannot use the equation of V, integration of rho s ds over 4 pi epsilon of r. So this equation cannot be used. Okay, so this is a strict regulation in calculating the potential for the case of a charge distribution which are said to be symmetrical, and the E field can only be obtained using the Gauss law. Okay, yeah, so hopefully you understand this. So you can only use this equation here to calculate the potential value. Okay, so let us proceed. If you want to use this equation of E dot dl, first of all, you need to use the Gauss law to find the E field. Then only you can proceed with finding the potential. Yeah? Okay, so let us proceed with finding the potential. Finding the E field first for this particular shell structure. Uh, so we are given this shell. Yeah, that is your R naught, your radius. This is your rho s. Okay, the first one is a position for R less than R naught. Okay, so basically for the Gauss law used, you need to sketch a Gaussian surface. Okay, so that's a Gaussian surface, which is for the R. Okay, and we can see that for this particular case, for this first condition, for the first region, for the R less than R naught, from D dot ds equals to the enclosed charge, it can be defined that the inner charge, the enclosed charge inside the Gaussian, yeah? Okay, this is charge at the Gaussian surface, enclosed charge is charge inside the Gaussian. We can see that the enclosed charge for this particular case will be equal to 0, and as such we can see that the vector D will be equal to 0, yeah, for the case of R bigger less than R naught. Okay, for the case of R bigger than R naught, which is for this particular Gaussian surface, okay, so that should be for a R bigger than R naught region. Okay, that should be your R, your radius for the Gaussian surface. So it can be proved that your d dot ds equation, okay, can be further written to be dr of 4 pi r squared, and the enclosed charge will be rho s of 4 pi r naught squared. Yeah, you can prove this on your own, yeah. Okay, because we know that the enclosed charge for the second case is only located here on the surface of your sphere or shell, so which is given by the area of 4 pi r naught squared, and as such you can find that the dr will be given by rho s multiplied with r naught squared over r squared, and further on we can write that the vector d will be rho s r naught squared divided by r squared direction of r, and we can have the E field to be equals to rho s r naught squared bahagi epsilon naught of r squared direction of r, volt per meter. Okay, so we have two value of E field now for the two region for r less than 0, sorry, r less than r naught. Yes, sorry for that. For r less than r naught. Okay, so we have the E field equals to 0. And then for r bigger than r naught, we have proved that the E field equals to rho s r naught squared bahagi epsilon naught divided by epsilon naught r squared direction of r. Yeah, volt per meter. Okay then. So from here, we can use the equations of E field here to calculate the potential for requested position in this question. So let us proceed with finding the potential for respective point of interest. Yeah. So I have to erase these terms first. Okay. So hopefully you understand, yeah, how to calculate the E field. Uh, so if you have a problem with this, so you have to go back to the Gauss law lectures. Yeah. Okay then. Okay. Right, so let's proceed with the first position, which is R naught over 2. So if I can sketch the shell, okay, that's your shell, that's your R naught, and the charge is here, rho s. Okay, so R naught over 2 is somewhere located here, so I have to use the red marker. So R naught over 2 is somewhere here. Okay, so that should be R naught divided by 2, the position inside the sphere structure. Okay, from definition of potential, yeah, where we have potential, let's say we define here as point of A. Potential at point A is defined to be negative integration from infinite to the point of interest of E dot dl. Okay, yeah, so that should be the equation that shall be used in calculating the potential. Yeah, so that should give us negative integration from infinite to A. So A is R naught divided by 2 of E dot dl. Okay, then, so which means that your initial point is here at infinite, yeah? If I can put at infinite is here. So we are moving from a infinite to the point of A. So a movement of charge from the point of A, sorry, from the point of infinite to the point of A will pass through two values of electric field. The first one is for the region of R less than, so R bigger than R naught, yeah, R bigger than R naught. And then further on, it has to pass through an electric field region, which is for the R less than R naught. So a movement from infinite to the point of R naught over 2 will require a movement of charge in two different regions of electric field, as mentioned here. The first one is from infinite to R naught, which is dealing with the E field here. Let's say we write this as E2. And then from R naught to R naught over 2, we have the E field number 1, which is 0. Yeah. Okay, so based on this argument, I can rewrite this integration to be equals to potential of A at A will be negative integration from infinite to R naught of E2 dot dl, okay, plus integration from R naught to R naught over 2 of E1 dot dl, okay, in which we have separate the equation, the integration, yeah, from infinite to R naught over 2 into two different integration. The first one is from infinite to R naught, dealing with the E2 region, and then from R naught to R naught over 2, dealing with the E1 region. Okay, so from here, we can proceed with the integration to find the potential at A. So the VA will be equals to negative integration from infinite to R naught of E2, which is rho s, R naught squared over epsilon naught of R squared, direction of R, and dl will be then returned to be dr, direction of R, yeah, to in which the E and dl must be having same unit vector. If not, we cannot find the integration, yeah. Whereas for the E1 dot dl, knowing that the E1 is 0 from what we have obtained previously for the E field, so that contribution will be 0. Yeah, because the E1 is 0, so we don't have to calculate the integration from R naught to R naught over 2. Yeah, so we just deal with this first integration here. So if we proceed with the integration, we're going to have the VA will be rho s R naught squared, because R naught is a constant, so it can be taken out, over epsilon naught, and that will give us 1 over R, which is integration from infinite to R naught. And as such, we're going to have the VA will be equals to rho s R naught divided by epsilon naught in volt unit. Okay then, so that should be the potential at the point of A, yeah? Right. Is there any question on this? Hopefully it's okay, yeah? Right. So for the second part of this question, which is to find the potential at R naught. Okay, so basically the method will be the same as before. So if we can erase part of this, so yeah. Okay, sorry for that interruption just now. Sorry for that. So if I can recall by the equation of the E field, yeah, we have for R less than R naught, we have E1 equals to 0. For R bigger than R naught, we have the E2 equals to, sorry for that. We have the E field equals to rho s R naught squared divided by epsilon naught of R squared, direction of R, yeah? Okay, so we sketch again your spherical structure to answer question 2 just now. Okay, right, that should be your R naught. Okay, so you need to find the potential at this position, which is at the surface of your shell. This should be the R naught, yeah? You want to find the potential at this position. Okay, so to find the potential at this position, you have to use the equation of VA. So I label this as a VA, yeah? As a negative integration from infinite to R naught of E dot dl. Okay, so again, you have to deal with the charge movement from infinite here. So when the charge is moving from infinite to the point of A. Okay, so based on this diagram, how many regions that need to be passed through by the charge? So obviously, you only need to pass through a single region, which is region number 2, yeah, region number 2. So this equation can be further written to be negative integration of infinite to R naught of E2 dot dl. Yeah, because we don't have to pass through region number 1, right? Region number 1 or E1 is inside the sphere. Yeah, so we only have region number 2, which is having electric field of E2. Okay, so we can proceed with the calculation of the E field, sorry, with the potential. You're going to have negative integration infinite to R naught, rho s R naught squared over epsilon naught of R squared dr, because dl is dr in the direction of R, yeah, dl is dr direction of R. So we can proceed with the integration, and up we're going to have the rho s of R naught divided by epsilon naught, same as what we obtained previously for the case of R naught divided by 2 in volt unit, yeah. Yeah, and then for the third case in which your position is at 2 R naught, yeah, so 2 R naught is somewhere here, yeah, that should be 2 R naught if I can connect this line. Okay, that is 2 R naught. Okay, so a movement from infinite, yeah, infinite to the point of a 2 R naught, because if you want to find the potential at 2 R naught here, potential at 2 R naught, let's say we define here as the point of A. So we have the point of A, potential at the point of A should be equals to a negative integration from infinite to 2 R naught of E dot dl. Okay, yeah. So integration will from infinite to the point of A. So A is having a distance of 2 R naught from the center of your sphere. So for this, you're going to have uh, integration, negative integration, negative infinite to 2 R naught of rho s R naught squared divided by epsilon naught of R squared dr. So as we proceed with these integrations, I'm going to write it here. Okay, so your potential at point A will be equals to rho s R naught squared divided by epsilon naught. Okay, that will give us 1 over R, yeah, from infinite to 2 R naught, and end up we're going to have the VA shall be equals to rho s R naught divided by 2 epsilon naught in the fourth unit, yeah. So that should be your potential at the point of A by using the equation of E dot dl, yeah. So we can see that this is the example on how to calculate the potential when we are having a symmetrical charge distribution in which the E field can be calculated by using the Gauss law. Okay then, hopefully you understand the method on calculating the potential here. So again, if you have any questions related to these exercises, related to this topic of potential, lecture number 8, do kindly contact me for further discussion, yeah? Okay, so that's all for lecture number 8. We're going to continue with lecture number 9 on Thursday, the topic of potential gradient and energy density in electrostatic field. Okay, with that, thank you very much.